Hello. Welcome to today's lesson on half-life calculations. We will explore how to determine the half-life of a radioactive isotope and calculate the remaining fraction of a sample after a given period. By understanding these concepts, you will be able to apply them to various practical scenarios in fields like medicine, archaeology, and nuclear physics. To remind you, the half-life of a radioactive isotope is the time it takes for half of the radioactive nuclei in a sample to decay. This concept helps us predict how a sample of radioactive material will change over time. There are two sorts of calculations you will be asked to do at GCSE level that relate to half-life. The first will be to find out the half-life of a radioactive sample, and the second will be to find out how much of a radioactive sample remains after a given number of half-lives. We'll begin with the first case. We are told that a sample initially contains 8,000 radioactive nuclei. After 20 minutes, the number of remaining radioactive nuclei is 2,000. We are asked to find the half-life of this sample. To do this, we divide the initial number by 2 until we reach the remaining number of nuclei in the sample. For this case, after the first half-life, there will be 4,000 nuclei, as 8,000 divided by 2 equals 4,000. After the second half-life, there will be 2,000 nuclei remaining, as 4,000 divided by 2 equals 2,000. Thus, 2 half-lives have passed. Since 20 minutes represents 2 half-lives, divide the total time by the number of half-lives to find the duration of one half-life. That is, half-life equals total time divided by number of half-lives. So in this example, we divide 20 by 2 to find that the half-life is 10 minutes. So the half-life of this sample is 10 minutes. Now let's consider the second kind of calculation we'll be asked to do, finding the fraction of a radioactive sample that remains after a certain period given the half-life. Suppose you have a radioactive sample with 1,000 radioactive nuclei and a half-life of 10 days. We are now asked to find the fraction of radioactive sample that remains after 30 days. To do this, we first calculate the number of half-lives. In this case, we divide 30 days by 10 days per half-life. This gives 3 half-lives. We can now calculate the remaining fraction of radioactive sample. Specifically, after each half-life, the sample halves. So in this problem, after one half-life, half the number of nuclei that remain is 1,000 divided by 2, which gives us 500 radioactive nuclei. After 2 half-lives, a quarter remains, or 1,000 divided by 4 gives 250 radioactive nuclei. After 3 half-lives, an eighth remains, meaning that after 30 days, the number of radioactive nuclei that remain is 1,000 divided by 8, which we can calculate to be 125 radioactive nuclei. Alternatively, we could simplify this calculation by using the formula that the fraction remaining is equal to 1/2 raised to the power of the number of half-lives. So for 3 half-lives, this is 1/2 to the power of 3, or 1/8 of the original radioactive sample remaining. Let's consolidate this new knowledge by going through some more practice problems. A sample with 6,400 nuclei decreases to 800 nuclei after 30 minutes. Let's determine the half-life. Firstly, we need to calculate the number of half-lives. 6,400 to 3,200 is 1 half-life. 3,200 to 1,600 is 2 half-lives, and 1,600 to 800 is 3 half-lives. Hence, the total time for 3 half-lives is 30 minutes. This means 1 half-life is 30 minutes divided by 3, or 10 minutes. Let's try another problem. A radioactive material has a half-life of 5 days. If we start with a sample of 16 grams, how much of the sample remains after 15 days? First, we need to determine the number of half-lives passed. 15 days divided by 5 days gives 3 half-lives. Next, we need to calculate the remaining fraction of the sample. After 1 half-life, half of 16 grams remains, which is 8 grams. After the second half-life, half of 8 grams remains, which is 4 grams. After the third half-life, half of 4 grams remains, which is 2 grams. Therefore, After 15 days, 2 grams of the original 16-gram sample remains. Let's try another problem. A sample of 1,600 nuclei decreases to 200 nuclei after 40 minutes. We want to find the half-life. First, we need to calculate the number of half-lives. To do this, we need to divide the initial number by 2 until we get to the remaining number. 1,600 goes to 800 in one half-life, 800 reduces to 400 in the second half-life, and 400 reduces to 200 in the third half-life. Hence, the total time for 3 half-lives is 40 minutes. This means the time for one half-life is 40 minutes divided by 3, which is roughly 13.33 minutes. For this problem, we want to estimate the half-life when a sample with 1,024 nuclei decreases to 16 nuclei after 45 minutes. Firstly, we need to calculate the number of half-lives. Dividing the number of nuclei in the sample successively by 2 gives us 1,024 to 512, 512 to 256, 256 to 128, 128 to 64, 64 to 32, and finally 32 to 16. Hence, 6 half-lives have passed. The total time for 6 half-lives is 45 minutes. Therefore, the time for one half-life is 45 minutes divided by 6, which gives us 7.5 minutes. Let's try one final problem. A radioactive isotope has a half-life of 4 years. If we begin with a 20-gram sample, what fraction of the sample remains after 12 years? How much mass is that? Firstly, we need to determine the number of half-lives passed. 12 years divided by 4 years gives us 3 half-lives. Next, we need to calculate the remaining fraction of the sample. The fraction remaining is half to the power of the number of half-lives. So in this case, the fraction remaining is 1/2 to the power of 3, which gives us an eighth. We still need to calculate the mass of the remaining sample. 1/8 of 20 grams is 2.5 grams. Hence, our final answer is that after 12 years, 1/8 of the original sample remains, which is 2.5 grams of the initial 20 grams. In today's lesson, we examined how to calculate the half-life of a radioactive isotope and determine the fraction of a sample remaining after a specific period. By understanding and practicing these steps, you can confidently approach problems involving radioactive decay and half-life calculations. This knowledge is essential for applications in various scientific and practical fields,